All right, let's jump right in. Just imagine for a second being able to ask your company's huge, complicated database a question just in plain English and getting a perfect answer back instantly. That's the dream of text to SQL, right? But with that kind of power, you've got to ask yourself a really important question. How do you know you can trust the answer?
I mean, think about that. Your AI assistant tells you sales are up a whopping 20%. You might be ready to pop the champagne, maybe hire new people, make huge budget decisions based on that one piece of information. But what if the AI just slightly misunderstood what sales means in your company, or it forgot to filter out returns? A tiny mistake in the query can lead to a massively wrong answer, and that could lead to some seriously bad business decisions. That's why figuring out how to evaluate these systems isn't just nice to have, it's absolutely critical.
You see, for any text-to-SQL system to be truly ready for prime time, it has to deliver on two promises. We can call it a dual mandate. First, there's semantic equivalence. That's a fancy way of saying, does the code it generates actually find the right answer to your question? And second, you've got operational robustness. Is the system reliable? Is it fast? Is it secure when people are actually using it? You can't have one without the other. You need both.
So let's start with that first piece of the puzzle, accuracy. It sounds pretty straightforward, but defining what a correct SQL query even is, well, it's way more complicated than you'd think. And the way people have traditionally measured this, especially in academia, just doesn't really work once you get into the real world.
The classic benchmark that you'll see in a lot of research papers is called exact match, and it's exactly what it sounds like. The AI generates a SQL query, and the test just checks if that string of text perfectly matches a pre-written correct answer, character for character. It's super fast, it's easy to run, but man, is it rigid.
And here is the perfect example of why that's a problem. Look at these two queries. One says amount greater than 1,000, the other says 1,000 less than amount. Functionally, they are identical. They will give you the exact same data every single time. But if you're using an exact match evaluation, one of them gets a big red X. It's marked as a failure just because the characters are in a different order. And that's where this whole approach just completely misses the mark.
And that brings us to a much, much better way of measuring things: execution accuracy. This metric doesn't care one bit about what the code looks like. It asks a really simple question. If you run the AI's query and you run the known correct query, do you get the exact same results back? Yes or no? This has to be the standard for any real-world application because it focuses on the only thing that actually matters: getting the right answer.
Okay, now this is where things get really interesting, because we need to look under the hood. You might think a text-to-SQL system is just one big call to an LLM like magic, but it's not. The systems you see in production are actually these complex, multi-step pipelines, and they have a surprising, deep connection to another AI concept you've probably heard a lot about, RAG.
So here's a quick tour of how it usually works. Your question comes in, and first it hits something called an intent router. That just figures out if you're actually asking for data or just making small talk. Then, and this is the crucial part, it does what we call Schema RAG to figure out which database tables are even relevant to your question. Only after that step does an LLM actually try to write the SQL code, which then gets run against the database to fetch your answer.
So why all this complexity? Why this whole pipeline?
Well, the reason is actually pretty simple. An LLM, just by itself, has zero idea what your company's database looks like. It doesn't know you have a customers table or a column called last_login_date. It's completely blind to the structure, the schema of your data. And that is the #1 hurdle you have to overcome to generate correct SQL. And this is where Schema RAG saves the day. You know how a normal RAG system retrieves relevant documents from a knowledge base to help an LLM answer a question? Well, Schema RAG does the exact same thing, but instead of retrieving text, it retrieves the relevant pieces of your database blueprint, the table names, the column definitions, how they're all connected, and it feeds all of that to the LLM as context. It's basically RAG, but for your database structure.
So think about what this means. These text-to-SQL agents are actually hybrid systems, right? They're part information retrieval system, like RAG, and they're part code generator. And if the agent itself is a hybrid, it means we can't just use one type of evaluation. Our testing strategy has to be a hybrid too, so we can check on both parts of its job.
Let's break down why. It all comes down to what they're grounded in. A standard RAG agent is trying to find the truth in these messy, unstructured chunks of text. It's probabilistic. But a text-to-SQL agent is grounding its answer in your database schema. which is a fixed, structured, deterministic system. The source of truth is fundamentally different, and that means the way we measure success has to be different too.
So that leads us to this clear two-part evaluation strategy. Step 1, we have to assess the retrieval part. We use classic RAG metrics, like Contextual Recall, to answer the question, did the system even find the right tables and columns to work with in the first place? Because if it fails here, the final query is doomed. Then, for step 2, assuming it got the context right, we use our T2 SQL metrics, like execution accuracy, to ask, did it write the correct code using that context?
This table really lays it all out beautifully. A text-to-SQL agent's primary output is code you can run, so its success is all about execution accuracy. A RAG agent's output is just text, natural language, so its success is about being factually grounded. This fundamental difference in what they produce and how we define success is why you need to think about them differently.
Okay, so we've talked a lot about accuracy. But if you're trying to run one of these systems in a real company with real users, getting the right answer is really just the beginning. That's just table stakes. We also have to measure things like reliability, security, and efficiency to know if it's truly ready for the big leagues.
Here are a few reliability metrics that are absolutely essential for building trust in the system. First, compilation success rate. Does the SQL it writes even make sense, or is it just gibberish that will throw an error? Next, hallucination rate. How often is it just making up table or column names that don't even exist? And this last one is so important. Query rejection rate. Is the agent smart enough to just say, hey, I don't understand that question, instead of guessing and giving you a wrong answer?
And we can't possibly talk about production systems without talking about security. I mean, imagine a malicious user types in something that looks like this. This is a classic textbook SQL injection attack. If your system isn't built to defend against this, an attacker could potentially view, or even worse, delete your entire database. The threat is incredibly real.
Luckily, there is a rock-solid defense against this, and it's called parameterized queries. This is a non-negotiable, must-have security feature. The basic idea is that it forces the system to treat anything a user types in as just simple data, never as a piece of code to be executed. It completely shuts the door on this entire category of attacks.
So at the end of the day, all these detailed technical metrics, they all roll up into these bigger business-level priorities. What you really care about is a high user success rate. Are people actually getting the answers they need? You care about latency. Are they getting them fast? You need deep tracing to debug problems, and you need to be A/B testing to prove that changes are actually making things better for the business. We're even seeing really advanced systems that reward the AI for writing more efficient queries that run faster.
Which kind of brings us back full circle to this big question. When we ask an AI to work with our data, what's more important? Getting the facts right or getting the code to run perfectly? As we've seen today, maybe the real answer is that you can't have one without the other. Maybe flawless execution and factual grounding are really just two sides of the very same coin. And that coin is trust.